Good morning, students. So what we were seeing in the last few classes is the following. I talked about how to prepare a polycrystalline material, which could also be used as a target material for thin film growth. I explained the process of how solid state diffusion happens between two entities. We took the example of magnesium aluminum oxide. You start with magnesium oxide, aluminum oxide, and if you take these two as two solid bodies, and if you make a reaction to happen, the reaction happens only at the interface. That's a point of nucleation. So that process of reaction will be very slow because the ions have to diffuse inside the solid. Of course, for diffusion, thermal energy is also required. That's why you need to heat the compounds to higher temperatures. So I said to enhance the process of diffusion, you break up these individual compounds into powder particles. Where if you have powder particles, you mix them up, so you're creating large number of nucleation sites. So that is a key to increase the rate of reaction. And diffusion is governed by a simple Fick's law. Fick's first law of diffusion shows that your J, diffusion flux, is equal to minus of d dou C by dou X. Here the dou C by dou X is a concentration gradient, D is the diffusion coefficient, and J on the left hand side is the diffusion flux. So the simple law is also known as Fick's first law. We'll see a little more about it when I illustrate how diffusion happens in solids. I also said that going down to the lower particle sizes that leads to enhancement in diffusion is the best way to increase the time in which a polycrystalline material could be prepared. But I also asked you to imagine if that process of reducing the size is extended to atomic level. That means the whole target is broken down to its individual atoms. Then you have, of course, you have this flux of atoms coming from the target towards the substrate. And then if they're all in the right mix, right, so to say, stoichiometric ratio, and if you provide proper heating of the substrate, so you can imagine that the same polycrystalline material that is broken down to individual atoms, you can then imagine that the reaction of these species would happen at a much faster rate. So if the time taken for preparing a polycrystalline target material is about a few days, those are the time scales normally, 3, 4, 5 days, because it, as I mentioned to you, the solid state reaction process involves heating up the compound several times in order to increase the homogeneity, and then the same polycrystalline compound that takes about a week or a few days to prepare, you can transform it into a thin film form, crystalline thin film form, within a few minutes. So that's the beauty of growing crystalline thin films of any material system. Okay. Now, what we'll see today is, I also mentioned that it's also important that since the temperature plays a crucial role, I also started mentioning about various ways in which heating is done. You have a typical box furnace in which material is kept and heated. Then you have a tubular furnace, and tubular furnace is a good alternative if you don't have a vacuum furnace where these metals and alloys, or intermetallic compounds have to be heated in oxygen-free environment, otherwise they get oxidized. So ideally, what is required is a vacuum furnace. But I mentioned that the alternative for that is vacuum furnace is an expensive perspective. So to overcome that, you use a tubular furnace, which means that you're still heating the compound in a tube with both ends sealed, and I can have an inert gas passing through it. That will create inert atmosphere devoid of any traces of oxygen. Okay. So I mentioned about heating elements. I said we have nichrome and canthal are the two most commonly used heating elements. Yeah. Whether you're constructing a furnace or whether it is you want to make a thin film heater meant for thin film growth. These heaters are very useful. With nichrome wires, if a furnace is wound with nichrome wires, you can get a maximum of 1400 degrees centigrade. And if it is canthal, you can go up to 1500 degrees centigrade. Suppose if the compound needs to be heated to much higher temperatures, beyond 1500 degrees centigrade, what do we do? Okay, that's what I showed you yesterday. When the current is passed through these coiled nichrome and canthal wires, they get heated up, and this color itself shows that you already have a temperature of above 800 degrees centigrade inside the furnace. Okay. So the next best is if you want to go beyond 1500 degrees centigrade, what you have here is a very useful heating material called silicon carbide. Yeah. This is silicon carbide. Silicon carbide basically is a semiconductor, right? It's a very useful semiconducting material with a lot of electronic applications. But silicon carbide is equally important while fabricating furnaces. So what is done is the silicon carbide powders are compressed in the form of these rods, and normally a small constriction is basically something like that. A constriction, and this is where you have a different resistance. So when the current is passed through this, you'll see this part getting heated up. That's what you see there. Yeah? You create a heating zone. And with silicon carbide heating, one can go up to 1600 degrees centigrade easily. Okay. Yeah, 1600 degrees centigrade. So beyond 1500 degrees centigrade, if you want to have temperatures above 1500 degrees centigrade, one has to use silicon carbide heating elements. You can go up to, push it up to 1650 to 1700 degrees centigrade. Now, if you want to go beyond this temperature, what do? You want to go above 1600 degrees centigrade, right? So that's why I said there is no single set of heating elements or one single furnace that can solve all the problems. So if you want to go beyond 1600 degrees centigrade, because there's some compounds that need to be heated at temperatures higher than 1600 degrees centigrade. Okay, I told you for sputtering you need really dense targets. So if the target material is a high melting point compound, if you heat the compacts at lower temperatures, then the compact will not have the required density, hardness, especially density. It will be very porous, and it's not going to serve any good purpose in the process of thin film growth, right? So you see that what you saw, okay, starting all the way from these coils made of nichrome and canthal. When you come to silicon carbide, it's typically used in the form of these rods. And then what you see here is also a U-tape rod arrangement. Imagine the diameter of the rod is also tapered off here, like what I showed here, right? And this is to basically, you know, make a little high resistance zone, right? When the current is passed, this area, this entire length of the rod in this U is going to be heated up, and that's what you see inside. These rods that are sitting inside, and when they're heated up, you see that high temperature being generated. But what are these rods made of? So if you want to go beyond 1600 or 1650, silicon carbide won't work. Then you use what is called it is called super canthal. Okay? Super canthal is molybdenum disilicide. Very useful, again, semiconducting material, molybdenum disilicide. Okay? It's called supercanthal because supercanthal can give you temperatures as high as 1800 degrees centigrade. Interesting, right? You see, all the way from nichrome to canthal to silicon carbide to supercanthal. So you can choose. So for general purpose heating at lower temperatures, you know, these two heating elements are sufficient. But if you're looking for anything beyond 1500, it's silicon carbide, and beyond that, it's up to 1800 degrees centigrade molybdenum disilicide. But molybdenum disilicide heating elements are very expensive in the sense that, well, the cost increases from nichrome canthal to silicon carbide to supercanthal. And also, as I told you, all these heating elements are continually subjected to thermal cycling. You're heating them up, cooling them, heating them, cooling them, several cycles, So over a period of time, the resistance changes. So when the resistance changes, the current, the input current has to change. So over a period of time, the performance of these heating elements will start deteriorating. So especially for a material like molybdenum disilicide, supercanthal, it is advised that such furnaces should not be turned off, which means if I'm heating something at 1800 degrees centigrade, it is always desirable to bring the temperature down to about 1200 degrees centigrade and leave the furnace there rather than shutting it off, which means the rods are cooled back to room temperature. So that process of taking it back to room temperature and again heating it to the highest achievable temperature causes severe what is called thermal damage to these rods. They become more and more brittle. That leads to the need for replacing these rods very often. So in a furnace like what you see there, typically we use about 4 to 10 such rods. So a single rod may be costing about ₹1,00,000. You can imagine how costly these furnaces will be. So as you want higher and higher temperatures, the money that is involved in constructing these furnaces or buying these furnaces will be on the higher side. Okay. Then, yes. So if you see this, yeah.
One question. Can we not use this silicon carbide as a coil?
You can. All these uh, different types of heating materials that I've showed, starting from nichrome, um, you know, starting from nichrome, 1 minute, nichrome, canthal, silicon carbide, and molybdenum disilicate. You can use them for making these big furnaces, depending on the requirement of the temperature, and you can also use them as substrate heaters. That's what I'm showing it here, right? You see it. This is a typical substrate heater that is used in a thin film growth process. If the inside of it is, you can see this, right? This is a coil made of one of these elements or alloys, and there's a top cover there, and you're passing a current through these ports, and then you can achieve the temperature that you require. As I told you yesterday, uh, in thin film growth process, you may not require the same temperature as that you use in a regular. So this is typically, these are connected to the pumping modules. So this is where you have the heater block. Okay, so that's the heater there. Understand? So if it is a simple thermal evaporation process, I have you have your charge there, okay, on the heater. So the heater is sitting there nicely. That. Now this is the substrate holder, or in the case of a simple thermal evaporation, I take a charge. Charge is in this case a piece of copper or gold or aluminum, and so when you start heating it using one of these heaters, what you see is this will start getting vaporized, and these vapors raise, and you expect these wafers to settle down on the substrate as thin film. That's the simplest way of understanding a growth process. So this thermal heating is very essential. Heating of the substrate is very essential, and it depends on what kind of. If it is simple thermal evaporation, so if I'm heating copper, certainly at least about 1500 degrees centigrade is required. Um, Copper melts at 1085 degrees centigrade, about 1100. So if it is iron, cobalt, nickel, anywhere from 1400 degrees centigrade to 1500 degrees centigrade. But in a normal thermal evaporation, when I explain the process, you'll understand. These heaters are normally used in the sputtering process and other thin film growth process. But the simple thing I explained here, thermal evaporation, it also uses exact coil heaters like that. Okay, so you'll understand all that when I actually start talking about the growth process. Yeah, the heaters can basically be made by any of these materials that I showed.
So
Okay?
if we are using a coil and a rod, is there a difference in temperature, the heating temperature
Yes.
maximum?
Yeah. You'll get depending on the amount of current that you pass through the coil material, right? And then depending on the number of turns also, you can vary the coil temperature. You can control the temperature also.
So maximum heating temperature that material can withstand. So can we say it is different for same material if we are using a coil and we are using a rod?
Yeah. What is the question?
So if we are using, suppose let's say silicon carbide, we are using it as a rod and a coil. So maximum heating temperature, would it be same for both of these?
It depends on the, so if you take the same silicon carbide, you see that. So here silicon carbide is taken in this form. Okay. Now it is taken in this form with small cuts. This is to increase the resistance. So you can get these rods and coils with a specific resistance value, and then you can calculate the current that is required to be passed through it. And for the given amount of that resistance and the current values, right? So you'll achieve certain amount of the heating temperature. This can be easily controlled. For the same material also, if I want to use silicon carbide for just heating a substrate or creating a temperature of just 800 or 900 also, I can use it. But normally, it's the same thing with molybdenum disilicide also. But as I told you, because of the thermal cycling problem that is involved, you don't want to use a molybdenum disilicide supercanthal heating element to create low temperatures of the order of 1200 or 1300. Then it is actually waste of this material. This is, it's preferred that molybdenum disilicide supercanthal is used when you want to go to these highest temperatures. That's why you have a range of materials that you can choose for heating, either in furnaces or for making, substrate heaters. Okay. Now, what do we do if we have to go beyond 1800 degrees centigrade? Suppose I want to make an intermetallic compound. I want to make an alloy first, and I want to use the alloy composition in a thermal evaporator. That means instead of this being copper or gold or platinum, I want to heat, say, an alloy, binary alloy consisting of two elements. So first, I need to fuse the alloy. I need to take these two elements and form the alloy, or the the compound I talked about, intermetallic compound, which is I gave a few examples: Nb3Ge, niobium vanadium. I also talked about an intermetallic. A good example is Nd2Fe14b, which is a magnetic, permanent magnetic material. So first, we talked about how to make this ceramic compounds, starting from individual compounds. You need to also make an alloy before you go for the thin film growth. But if you have to melt tungsten, for example, tungsten has a melting point of 3,400 degrees centigrade. Right? And some of these are called refractory elements. They have very high melting point, about 2,500 degrees centigrade. Molybdenum, rhenium. So how do you make alloys containing very high melting point elements? Right? These are low melting point elements. So you can't use even supercanthal in that case. Of course, one useful way of melting, as I told you, is again take a high melting point element, make it in the form of coil. I use the coil heater to heat those high melting point elements. But to make an alloy composition or the interatomic composition beyond 1800 degrees centigrade, what you need is what is called the arc melting. In the process of welding very high temperatures are created. Arc, the process of arc melting. So a typical arc melting unit looks like this. This is a main unit, and these are all the associated, pumping modules. It's a very interesting way of melting two elements. So if I have one element there, it's say there's one there. So I need to fuse these two into one single alloy composition. It's a challenge because the melting points are very high of one of the elements, say, unless you melt both of them, the alloy won't form, right? So if A has a melting point of, say, 1800 degrees centigrade and B has a melting point of 2200 degrees centigrade, unless you generate a temperature of 2200 degrees centigrade, B won't melt. So unless both the elements melt, alloys won't form. This is always a challenge when you start start dealing with high melting point elements to make alloys and intermetallics. So arc melting unit, arc melting process comes handy. It works on a very simple principle. Now, if you see this, it has a top handle there. This is the one. Yeah. This is something like a movable electrode. See, this whole thing is again inside vacuum. This whole thing is evacuated first. That's where you have the vacuum pump here, right? And of course, we are talking about making an alloy. You don't want any traces of oxygen. So first thing is you create this enclosure, right? And then you create vacuum by using the pumping module. So at least 10 raised to minus 6 torr of vacuum level inside this arc melting unit is good. Now, how do I generate high temperatures? This process I'm telling here because it's also useful when you understand one of the thin film process. It's very interesting. Now, what you have there, here, so this electrode here is what you're seeing there, and somewhere there you have this portion. So you draw it this way, yeah. Something like that. And I have an electrode coming from the top, and this is a copper hearth. This itself becomes an electrode. Okay. Now, this electrode I can rotate. I can move it like that, right? Now imagine it's a pointed electrode. As you can see here, it's a clearly pointed electrode, which I can move its position like that. There's a special arrangement here. There are certain seals. Look, this whole bell-shaped jar that I've drawn here, or what you see here, the challenge of vacuum components is when you have vacuum inside, it's not easy to have couplers that can also move around. But there are certain components, because this is connected to the vacuum chamber, right? There are certain seals through which, if you have a rod-like arrangement, you can make that rod to move without breaking the vacuum. You can imagine, right? This is the surface, and this is a rod we are talking about, and then I'm moving it. Why we have to move it? So this movement should not lead to any break in the vacuum. So you have special seals, and then this seal will take care of even this movement to a certain extent. Okay. So the whole idea is the following. If I have if you have these two elements which needs to be fused, let's say about 2300 degrees centigrade, which you cannot achieve with the normal furnace elements that I talked about, you need to generate those high temperatures inside this volume. So if you go back to this one, so this is like a block like that. Yeah. So inside this block, this is made of copper. It's a copper block. It's called the copper hearth. Inside of it, you have a small piece of alloy 1 or A, B. Right? So this block, as you can see, it has a small depression there. So that small depression. So depending on the capacity of the arc melting unit, you'll be able to melt 5 grams, 10 grams, 50 grams, and larger amounts also. But the process is what is important for you to know. So how I create these high temperatures there? So first I evacuate it down to 10 raised to minus 6 torr. Okay. And that's not the end of it. So the name itself suggests that it's arc melting. That means I need to create an arc inside. It's like welding, the process of welding. At the point where welding happens, you see very high temperature is generated. There also it's a process of melting, two pieces of metal, and then during the cooling process, they get fused. Or sometimes an additional element is also used. Okay. It's something very similar, and there also you'd have seen when welding is done, a very pointed tool is used. So that's where this the top electrode is very useful. That is, top electrode is made of tungsten. Tungsten is a high melting point element. Tungsten has a melting point above 3000 degrees centigrade. So it doesn't, so the electrode itself doesn't melt easily. See that? There's the pointed one there, right? And you see the copper hearth that I've drawn here, the green block is exactly there. And you see what is shown there is, it has several of those dips, right? It's like a steel plate with different compartments, one for the curry, one for something else, and so on. Okay, exactly like that. Now you can imagine that you have one element there, one element there, one there. You can see that clearly. One minute, I'm just trying to. Okay. Screen sharing has stopped. Okay, I'll go back to screen sharing. All right. So, yeah, see that? It's clear now. So, the electrode that can be moved around, and then if you have 3 elements to be fused or 4 elements to be fused, you can keep them all in those small compartments. So what happens in reality is the following. So you're passing a very high current. So this is an electrode, and the bottom, it's a block, it's like a copper block with those depressions, is also an electrode. And you pass a current of about 60, 70, 80 amperes between the electrode and the copper block. Now, because I can move the electrode, I can take it close to this stationary electrode, that is the copper block there. Yeah. So what I have drawn here is, let me try it again. So this is the electrode, this is another electrode, okay? One electrode and the other electrode. So I can bring it so close and I can also move it around. Okay. This electrode I can move around. Now, how do you create an arc? So I said first you evacuate it down to 10 raised to -7 torr and -6 or -7 torr. So there are no traces of oxygen. And then we have argon gas inside. We pass a little amount of argon gas. It's an inert gas. And so you have the gas present inside, right? Now the moment you bring it close, so at that point, so this electrode is brought close to the electrode where effectively you need to do the melting of the two elements that are present there. So within a small gap between the top tip, right, this electrode, and the stationary one, the moment you bring it within a few millimeters of distance, okay, and since you're passing such a high current between these two electrodes, and argon is present there, so the neutral argon ionizes instantaneously. And of course, ionization of a gas is a very common process. We know that you need to have all these, you know, the neon sign lamps that you see is nothing but you strike an arc and then you ionize a gas and the gas glows. Simple. We are using the same process here, except that I want to generate that ionization in a very small volume so that I'll have a concentrated heat at a certain point. That's the whole idea. So, so the electrode that comes in there, and it's so close. Now I have a very high current between the electrode, the two electrodes. And because this is pointed, I can also have two electrodes which are parallel to each other, like in a parallel plate capacitor. And if I have gas flowing in between, and if I have a high potential between these two electrodes, one is a positive terminal, other is a negative terminal, right? This also leads to the process of ionizing the gas molecules or gas atoms present in between the electrodes. It's exactly the same thing happens. So I have this electrode now, except that the ionization process happens at a very specific point, and that is there. And that's enough. So the moment the gas ionizes, then you see the formation of plasma. And this plasma temperature can be extremely high, about 2500 degrees centigrade, which is sufficient to melt most of the elements. See that? That's a beautiful way of, so you can move also, you can melt that part, go more to the next one, third one. So in one shot, you'll be able to make 3-4 sets of alloys, because once you create a vacuum, you'd like to make best use of that, and in one shot, depending on the capacity of the hearth, because the top electrode is movable. It's a very versatile way of creating local temperatures leading to melting of most of the elements. So for making alloys and intermetallics, there is no other better way, right? It's having these simple units is affordable. You can have it in the lab level, right? Well, when you're here around, I can show you this unit, and also you can actually see how it operates. Sometimes not sometimes, you can also have a glass enclosure or a glass viewport. You see that one of this is a viewports, and you can actually see what is happening inside. Once the plasma is struck between the electrodes, you should actually be able to see the plasma forming there. And then immediately you'll also see both the elements melting, flowing into each other. And then when you remove the electrode a little away from it, the plasma stops, because and then because you increase the distance between the electrodes, and then the alloy formation is complete, and you can take it out. The question here is, the alloy or the intermetallic that is formed in this process is very instantaneous. You take it close to the two elements or three elements, and within a certain short distance, the arc strikes, high temperature is created, elements melt, and by even you can, with the same electrode, you can sort of mix the molten mixture. A little bit of doing like this will make sure that the molten parts of A and B move into each other, and so you have the formation of the final alloy here, or an intermetallic with a specific composition. But there are many issues here. One is, if there are the melting points of A and B are largely different, then the problem is the first element that has a lower melting point starts evaporating faster. It'll come out first. And so you're vaporizing element A much faster than element B. So in the final composition, there could be a problem of having A atoms in lesser quantity. It means the final alloy composition will have deficiency in A or B depending on the vapor pressures. This is where the vapor pressure plays a very crucial role when we talk about making compounds, alloys. Even in thin film growth, you'll understand vapor pressure plays a very, very crucial role. So there's a way to deal with this. When we actually look at the thin film growth process, you'll see. But then this is how alloys are made. And once you get an alloy, now two entities have become one, right? This is now a single entity, a piece of an alloy that you get it from these two pieces of elements, you get an alloy. But Mike, if I ask you a question, if this alloy that is formed out of A and B, will it be crystalline or not? That means if I go and do X-ray diffraction on this one, just after using the arc melting furnace or unit, I form an alloy from A and B. My question is, will this be crystalline or not? So I know how to do it, right? You take this alloy and put it in an X-ray diffractometer. That tells me whether it is crystalline or not. Will it be crystalline or not?
Yeah, crystalline, sir.
Sure?
Yeah, sure.
How sure are you about it?
Polycrystalline, sir.
Huh?
Polycrystalline.
Polycrystalline, one answer. The second answer is...
I'm telling based upon my experience. I've done arc melting twice and it was polycrystalline.
yes.
Once it was terphenol and otherwise I forgot the alloy. But
Yeah.
it was polycrystalline.
Yeah. Well, and the other answer is crystalline. How do you say it's crystalline? See, don't you see the similarities between this process and what I explained about the single crystal growth? I said you take the material to its melting point and rapidly cool it. You don't allow the material to form into its crystalline form, is it not? Because you're not given enough time for the atoms to settle down to their lattice positions, right? So that leads to the glassy formation, is it not? So you rapidly heat the material to its melting point and rapidly cool it to room temperature. So it should lead to not so crystalline form. So in most of the cases, you get the metal in a non-crystalline amorphous state, But if these elements, if this is a process that you subject a ceramic to, where ceramic compounds are heated to high temperature and rapidly quenched to room temperature, no crystallization happens. In ceramics, if you don't give enough time for the lattice to form, there is no question of formation of crystalline lattice. Even polycrystallinity won't set in if these are not alloys. But in the case of alloys, these are metals basically, right? Metals don't have directional bonds. So even if you rapidly cool it, right, some sort of formation will be there, but not to the extent that you see single crystallinity. First of all, one thing you should understand, you cannot make single crystals out of metals. There is, do you know of a single crystal of gold or silver or copper? No, there are no single crystals. Single crystals of barium titanate, gallium arsenide, silicon, right? Other 2,5-2,6 compounds. You can talk about single crystals of those materials. Yttrium copper oxide, which is a superconductor, which is also a ceramic, you can get it in a single crystalline form. But we don't talk about single crystals of metals. You know why? Because metals do not have directional bonds. The bonds in metals are completely non-directional. In a crystal, the bonds are directional. That's why I can identify a particular crystallographic axis and say, yeah, when I stack all the unit cells, this is my 100 direction. This is my 111 direction. Specifically, you can say that. But metals and alloys, no directionality. Metals have no directional bonds. So that is why you cannot grow crystals, single crystals out of metals. This is a very important point. Okay? So, and that's the reason why, because metals do not have directionality in their bonds, they're malleable and ductile, right? You can get shapes out of metals in the way you want. And you can't shape a ceramic. If I have a ceramic, of course, I can get a very dense ceramic. Of course, the bonding in ceramic compounds it could be covalent or ionic or a mixture of both. And ionic and covalent bonds are stronger than metallic bonds. But then ceramics are, brittle. So they can just break and with a certain high force. But this breaking happens along crystallographic axis, certain crystallographic axis. Metals, you can't break down, right? If you apply a large force on it, after heating, you can shape them. That's a beautiful property of metals, the so-called malleability and ductility, which is not there in the case of the ceramic components. Okay, so so if you want to induce better crystallinity right after the arc melting process in these alloys and intermetallics, you again have to heat this final alloy composition at a certain high temperature, followed by slow cooling process, exactly like we do in the case of polycrystalline material, where the last process of sintering of that, compressed powders, to get it in a solid form. So this already exists in a solid form. The moment you subject it to the arc melting process, take the electrode out, you see a solid piece of the alloy. There's no problem. But then if you want to induce more crystallinity, you need to heat it to certain high temperature and cool it. And that doesn't make it transform into a single crystal. You see it still as a polycrystalline system. That means all X-ray Bragg reflections you see, because metals will not give single crystallinity because there are no directional bonds. So I'll just stop with this. So if you have a single crystal, like what you see here, single crystal has you're expected to see perfect periodic order in all 3 dimensions, extension of perfect crystallographic structure in 3 macroscopic dimensions, and the extension of periodic order in all dimensions. In the case of a thin film also, it's called crystalline thin film or an epitaxial thin film, except that thin films do not have this kind of volumes, right? So along all the three principal axes, you can talk of a 1 centimeter cube single crystal, but here I can't talk of a 1 centimeter cube single thin film. It could be 1 centimeter square in area, and the thickness has to be limited to not more than half a micron. Beyond that, the crystallinity will not be there. Polycrystalline materials can be bigger in size, like single crystals, but then in polycrystals, you have this problem of grains and grain boundaries. Okay? And I keep emphasizing this: presence of defects in crystals and thin films can influence physical properties, electrical properties, mechanical behavior, chemical reactivity. All these can be heavily influenced by the presence of grain boundaries. So you want material systems without the presence of grain boundaries. That's why we go for single crystals or thin films. Okay, I think I'll stop there, and we will meet again on Monday.